Okay, sir.
From the beginning.
Yes. Okay. I will repeat it one more time in this one, relationship. Okay.
Repeat from the beginning.
So in today's class, we will be studying about the relationship connecting the Young's modulus, bulk modulus, and the Poisson's ratio. Okay, Young's modulus is represented by Y, bulk modulus is represented by K, and Poisson's ratio is represented by sigma. Okay, and we all know that Poisson's ratio is a ratio of the lateral strain per unit stress. Okay, which is denoted by beta, to that of the linear strain per unit stress, which is denoted by alpha. Okay, so sigma is equal to beta by alpha. Okay, beta by alpha. Okay, so make this as one equation. Okay, keep it as equation number 1. Okay, so we will be using this at the end. Okay, when we connect it with the Young's modulus. Okay, I will write it here on the board. Okay, sigma is equal to beta by alpha. So let's put it as equation number 1 here. Okay, now Poisson's ratio is nothing but the relationship between strain to strain. Okay, so but the strain, as I said in the previous video, it is nothing but, suppose there is a wire, and if you're giving a weight, trying to give a force, and then you're trying to increase the length. Okay, the wire can undergo a change in the length. Okay, there may be a change in the length from the initial equilibrium position. So that increase in the length is given by this term as a lateral strain per unit strength. This will cause an increase in the length. Okay, increase in the length. That is a numerator for this one. And at the same time, the diameter of the wire will undergo a contraction. Okay, so that contraction, the difference in the diameter or the contraction taking place on the other side. Okay, contraction, increase in the length happens. Okay, and I hope you're not able to see. Let's suppose you have a wire, and okay, you're giving an extension along one side. Okay, along the length, okay, from the equilibrium position, the length can increase. Okay, so I can say the increase in the length of the wire, okay, is given by the lateral strain per unit strength. Okay, this will be an elongation process. Okay, and at the same time, okay, there will be a contraction in the diameter of the wire, which I will call it as the, okay, the increase in the length, okay, is given by alpha. Okay, and at the same time, beta is the, this is a contraction, sorry, this is a contraction. Sorry, this is a contraction, and this is a elongation. Okay. The beta is a contraction portion, that is a decrease in the diameter. Okay, and alpha is an increase in the length, which is called as an elongation. Okay, keep that in mind. Alpha is the increase in the length, beta is a contraction produced on the other side. I hope you're able to see the other side. Okay, with this basic idea, we are going to move on to the Young's modulus. Okay, I'm giving the preliminary introduction about the Poisson's ratio, because we are going to see this in the next continuation of the Young's modulus. And also one more relation between alpha. Okay, alpha is what? The linear strain per unit stress, isn't it? Okay, now how is the Young's modulus related to Poisson's ratio? Okay, it is related in this way as y is equal to 1 by alpha. Okay, how is it possible 1 by alpha? Alpha is nothing but what? 1 by alpha. Okay, alpha is what? The linear strain per unit stress. It is a ratio of the stress by strain itself here. Okay, so I have to write it here. It is a linear stress by linear strain, isn't it? Okay, so if I take it on the other side, it's going to be 1 divided by this value, which is nothing but, okay, which is going to be, linear strain by linear strain per unit stress. Isn't it? Okay, let me find this now. Y is equal to 1 by alpha. Okay, alpha is what? Linear strain per unit stress. Okay, so this is going to be linear strain per unit stress. Okay, if you take this term on the numerator, it's going to be Y is equal to linear stress by linear strain. Okay, which is nothing but equivalent to the Young's modulus itself. Okay, so I can relate the Young's modulus and the Poisson's ratio as, okay, I can relate the Young's modulus and the Poisson's ratio as 1 by sigma. Okay, so the Young's modulus is related to the Poisson's ratio by this relationship. Let's put it as equation number 2. Okay, so then I hope it's clear to you. Okay, next one. Always remember, alpha is the increase in the length, which is related to the elongation, and beta is related to the contraction. We are going to use this concept in a cube. This I explained it with respect to a wire, okay, which undergoes an elongation on one side, okay, and then a contraction on the other side. Now the same concept, I'm going to use it for a cube. Okay, so we will go into our exact this one with this preliminary equation. So what was the previous equation? One was beta by alpha na, is equal to sigma. Okay, Poisson's ratio is related to the ratio of the contraction per unit, this one unit length, divided by the elongation per unit length. Okay, so this was our first equation. This was our second equation. Okay, keeping this in mind, we will come back to our exact study. Okay, so these are required for connecting this relationship of Young's modulus, Y, K, and sigma. Okay, first I have explained the relationship between Y and sigma, isn't it? Y and sigma, I have explained it. So for how the Young's modulus and sigma are related to one another. Okay, now we will go on with the how the Young's modulus is related to the bulk modulus. Okay, so to do that, let's consider a cube. Okay, which is having the equal length on all the sides, so that its area will be a unit area. Okay, so we are going to consider a cube okay, with the edges as A, B. Okay, this is C. It's there in the book also. This is C and D. Okay, A, B, C, D, and the other side of the edge is E, F. Okay, and this will be G. This will be H. A, B, C, D, E, F, G, H. Okay, and imagine that I'm going to apply a tensile force. Okay, I'm going to apply a force. It's an unit cube. This is a unit cube, means okay, it is having the equal length on all the sides. Suppose imagine that L. Okay, it will be L on all the sides. So L can be a cubic, a unit cube. They are saying that means the volume of the cube will be L into L into L. Okay, which is going to be 1 into 1 into 1. The edges. Okay, it's going to be 1 cube, which is going to be 1. Okay, so the volume of the cube is an unity. Okay, so I will call this as a unit. The cube is supposed to have a unit surface area. Okay, so consider, okay, a cube having a unit surface area with a volume of 1, with a volume 1. Okay, volume is going to be 1. Okay, volume of the cube is going to be 1. I have taken it. Okay, take it as 1. Okay, now let us consider that a force is applied on one side. I have already told that if we are taking a wire and we are going to give a force on one side, okay, the length is going to increase and the diameter is going to decrease, isn't it? The increase of the length, I call it as a linear strain, and the contraction, I'm calling it as beta. Okay, so since I've already explained, I'm not going to explain. Now, this is with respect to your wire. The same concept is going to be applied to your cube, because we are going to now find the relation between the bulk modulus and Young's modulus. So we are starting with the cube, considering the need for the finding of the bulk modulus for a materials. Okay, since we are dealing with the bulk modulus, I am considering a cube, and then we will relate later on to the Young's modulus. Okay, so the volume of the cube is 1, and let's see how the volume is going to change when a force is going to be applied, okay, on the one side. Okay, so understand that we are going to apply a force. Okay, with the force, let's see that I'm going to apply a force along this side as Tx. Okay, along the x side, I'm going to apply a force which is Tx. Okay, a force of Tx is being applied along the x side. Okay, so what will happen to the other side? Other side, what will happen? There will be a contraction, isn't it? There will be an opposite force that will be acting. Okay, there will be an equal and opposite force that will be acting along this side. Okay, now in this side, if this is happening, what will happen to the other side? Okay, Tx is a force that is acting along one side. Now, what will happen to the y and the z direction? Okay, this is the x direction, y direction, and the z direction. Okay, so in the z direction and in the y direction, automatically there will be a contraction that is taking place. If you are giving a force along the x direction, then there will be a contraction that will be happening along the y and the z direction. Okay, so I'm going to put it in the equation form. Okay, so here again, one more time I will explain. So let alpha be the increase in the strain, alpha be the increase in the strain. Okay, increase in the strain per unit. Okay, per unit stress along the direction. Okay, along the direction in which the force is being applied. Okay, and beta. Okay, underline the word increase, or I can say elongation. Okay, beta is a contraction. Beta be the contraction. Contraction will be always minus, isn't it? Negative. Okay, contraction happening per unit length. Per unit length, per unit stress. Okay, in a direction perpendicular to the direction of the stress. Beta and alpha has a directional difference in the direction. Okay, they are perpendicular to each other. Keep that in mind. If the force is acting along one direction, there will be a contraction happening along the other direction. So I have to write it that per unit stress perpendicular to the direction of the force. Okay, perpendicular to the direction of the force. So beta will be minus. If alpha is a positive value, beta is going to be a negative value. Okay, so Tx is associated with the elongation, so alpha and Tx have to be multiplied, and similarly Okay, beta is a contraction happening along the y direction and also in the z direction. So I will have to subtract alpha tx minus beta ty and beta tz. Okay, I will write it in the equation form. Okay, I hope this is clear to you. Similarly, in the second case, we are going to see, okay, the direction will be changed and we will be applying the force along the ty direction. If you apply the force along the ty direction, automatically in the tx direction and in the tz direction, there will be a contraction that will be happening. Okay. Similarly, when I apply a tangential, when I apply a force along the tz direction, okay, I will write it here. When I apply the, so here I will write this equation as first one is if there is an elongation along this along the direction of tx, okay, alpha has to be multiplied with tx minus beta contraction happening along ty and beta contraction happening along tz. Okay, t beta tz, right? Similarly, okay, when I apply a force along the y direction, then along the x direction and along the z direction, there will be a contraction. So here I will put it as the second equation will be, okay, tx alpha. Yeah, I will write it in the proper equation form. Okay, so shall I rub this one? Okay, so the length of the edges, okay, along the edges AB. Okay, where is A and B? Along this edge, along this AB edge, whatever is happening, let us write it. Okay, so the length of the edge AB. Okay, the length of the edge AB becomes, okay, the initial volume of the cube is 1, okay, so it's going to be 1 plus, okay, it's going to be 1 plus of, okay, tx alpha, okay, minus of ty beta minus of tz gamma. No, tz beta, sorry, tz beta on x. Okay, beta is a contraction happening along the y and the z direction. Okay, this is for the edge AB. Okay, now similarly for the edge, okay, B and G. Okay, B and G is along the y direction, isn't it? B and G is along the y direction. Okay, so I will write it. Okay, see the figure. I'm going to now take it for BG and also I'm going to take it for BC. Okay, BC is along the Z direction. Okay, BG along the Y direction. Okay, so shall I rub this figure for a proper writing? Okay, so the same thing, the length of the edge. Okay, length BG. Okay, B to G. B to G is along the Y direction. Okay, so Y direction, and B to Z, B to C is along the Z direction. Okay, so will become BG is along for, this is for the X axis side, this is for the Y axis, and this is for the Z axis. Okay, for the three edges, so I'm not rubbing this figure so that you will see BG. Okay, for the length of the edge BG will now become, okay, 1 plus, okay, similarly it will become TY. In the TY direction, in the Y direction, there will be a elongation. So I will put it as positive for TY. Okay, because there is an elongation along the Y direction and there will be a contraction along the other direction. Say, I have to write it as X. Okay, TX side there will be a contraction, and also TZ direction there will be a contraction beta. I hope the video you're able to see. I will write it one more time. Okay, for T BC it will be 1 plus, in the BC it is the Z axis direction, isn't it? So I will write as there will be an elongation along the Z direction. Okay, at the same time there will be a contraction along the other two direction as TX side. There will be a contraction, and also TY side there is a contraction. Okay, I hope this is clear. Okay, now I will rub this figure and I will write it properly for because the board I'm not able to see. Okay, so that the length of the edge AB becomes, okay, I hope it's clear to you, 1 plus, so AB will become 1 plus TX alpha minus TY beta minus TZ beta. Okay, increase in the length along X direction and the contraction along the Y and Z direction for X axis, okay, along the edge AB. Now similarly for BG, which is going to be the Y axis, okay, it's going to be 1 plus of TY. There is an increase in the elongation along the Y side, which I put it as TY of alpha. And if there is an elongation on Y, there will be a contraction along the X direction, TX beta minus T Z beta. Okay. Now similarly for the edge, this is BG, this is BC will become 1 plus TZ. There will be an elongation and there will be a contraction along the other two edges. Okay, since this is on the very corner, I'm writing it here. Okay, the length of the edge AB, BG, and BC we have found it out. Okay, now we need to calculate the new increase in the volume of the cube. The volume of the cube was initially very perfect, isn't it? With a volume as 1. Okay, it was perfect. And after giving the force, no more the cube will have the same volume, isn't it? The volume will change. Okay, so we need to find the increase or the change, the new volume we need to calculate, and then we will subtract the new volume minus the old the initial volume, and then we will find the difference in the volume. Okay, so that is what we are going to do. So the increase in the volume of the cube, okay, the volume of the cube increases. So to find the new volume, okay, to find the new volume, what we need to do is multiply all these factors together. Okay, so this is this one along the edge AB, BC, and BG and BC, set along X and Y and Z. So multiply this to find the new volume. Okay, so I will write it in the equation form. We are going to multiply this one as, okay, one more time I have to write it. Okay, so AB into the new, to get the new volume, we need to multiply this factors into this factor 1 plus, okay, TY alpha minus TX beta minus TZ beta, okay, into 1 plus TZ of alpha minus TY beta minus TX beta. Okay. And this is a very huge multiplication. If you multiply it, you will have more than 27 factors. Okay. So, but let's simplify because there will be square terms and things, and that can be neglected. Certain values can be neglected, and simplified values can be taken in. Okay. Let us not go into much detail about the mathematical portion here. Okay. Simply, I will give you the final value of it, which is given in the book as 1 plus. Okay. 1 plus of the final value will come to be 1 plus alpha minus 2b into, okay, Tx plus Ty plus Tz. Okay, it is Tx plus Ty plus Tz. Okay, so this factor is a new volume. Okay, so shall we put it as some equation number 3? Okay. Now, this equation is obtained after neglecting the squares of the small quantities of alpha and beta. Okay, and if the value, okay, of tx and ty and tz's are very, very negligible and very small, okay, then, okay, we can take it as tx can be approximately equal to ty, approximately equal to tz. Okay, so we can take it as, okay, directly as a t. Okay, okay, approximation of t here. Okay, so the volume of the cube will now become, okay, 1 plus alpha minus 2 beta into this factor will become what? 1 t plus t plus t. Okay, will become t plus t plus t. It's an approximate value because the increase in the length or along the x, y, z is equal, and so they are taking it as t itself. Okay, so this will become 3t. So it will become 1 plus, okay, alpha minus 2 beta into 3t. Okay, so I will write this as equation as, let me put this 3t in the front. So I will put it as 1 plus 3t into alpha minus 2 beta. Okay, block this equation. Okay, and I will put this as equation number 3. I think that will be better. Okay, let's put this as equation number 3. Okay, the new volume is going to be 1 plus 3t into alpha minus 2 beta. Okay, now so this will be the increase in the volume of the cube. I'm going to write it one more time. The increase in the volume of the cube. Okay, the increase in the volume of the cube is equal to therefore the increase in the volume, okay, the difference of the original value and the final value, isn't it? So I will put it as this factor. Okay, this is the final volume. What is the initial volume? It is 1, isn't it? So the increase in the volume of the cube will be the final volume. So minus the initial volume. What we have found in equation 3 is the final volume after the stress is being applied, isn't it? So this is going to be the final volume, isn't it? After applying the force. What is our initial volume? It is a unit cube, so it is 1. Okay, so the final volume will be 1 plus of 3t alpha minus 2 beta minus the initial volume will be equivalent to 1. Okay, this 1 and 1 will go off. So you'll be left with the 3t into alpha minus 2 beta. Okay, so the increase in the volume is given by 3t into alpha minus 2 beta. Okay, hope it is clear to you all. Okay, I will rub it off. Okay. Now, this is related to the bulk modulus. Whatever we are doing is, we have taken the cube, okay, and we have applied a stress on one side, and we found the elongation happening along one side and the contraction along the other two sides with respect to x, with respect to y, and with respect to the z direction. We have done it. We have got 3 equations, and then we multiplied it to get the new volume, and the new volume was this one, and the initial volume of the cube, I said in the beginning, it is a unit cube 1. Okay, so the difference in the volume, or I can say the increase in the volume of the cube is equal to, okay, 3t into alpha minus 2b. This is related to the bulk modulus. So far, whatever we are doing is, we are doing with respect to the bulk modulus by applying a by applying a force on the three sides. Okay. Now we will have to connect it with respect to the Young's modulus. What is our aim? Our aim was to connect the Young's modulus and the bulk modulus, isn't it? So we need to go with the bulk modulus equation. So what is our bulk modulus equation? Okay. What is our bulk modulus equation? Bulk modulus is given by, okay, this is actually the equation 3. Okay. The bulk modulus is equal to volumetric stress divided by volumetric strain. Okay. And what is volumetric stress? We have applied the force, but if the force is taken per unit area, and initially I said that we are applying the force per unit area along the x, y, and z direction. Okay, so force per unit area, that is what we did it in the initial one, which is equivalent to nothing but stress. I will put this factor as T. T is a stress that is being applied. Okay, now what is the volume? Strain. Okay. The volume strain is calculated in this case with respect to the difference in the final volume to that of the initial volume. Okay, so therefore this is directly being taken as the equation 3. Okay, what was our equation 3? Okay, the one we calculated as 3t alpha minus 2 beta. I'll write it here. Okay, bulk modulus K is equal to T divided by 3T into alpha minus 2 beta. This factor was calculated in the way that we did, okay, by finding the difference in the change in the volume directly, okay, as a strain factor. Okay, so now this is going to be T, and T will be cancelled, and you will be left with what? K is equal to 1 by 3 into alpha minus 2 beta. Okay, so I will find that K is equal to 1 divided by 3 into alpha minus 2 beta. Okay, this is a very, very important relationship. Okay, so now we have got the bulk modulus in terms of alpha and beta only. Okay, so how are we going to relate it with the Young's modulus? Our aim is what? We need to find the relation between bulk modulus, Young's modulus, and the Poisson's ratio. But whatever we got, it is alpha and beta. Alpha, the factor you know as it is nothing but the alpha is nothing but the increase in the strain per unit stress along the elongation side. Beta is a contraction factor, isn't it? Okay. So knowing this, now I'm going to make this one. I will divide the numerator and the denominator by alpha. Okay. In order to connect this relation with the Young's modulus, I'm doing it. Okay. So divide the numerator and the denominator of this equation. Okay. Divide this numerator and the denominator by alpha. On both the sides, I'm going to divide it. Okay, so what will happen to this equation? Numerator, I'm going to divide it by alpha. Okay, and then denominator also, I'm going to divide it by alpha. Okay, is that clear to you? On both the sides, and the numerator, I'm dividing it by alpha. Why I'm doing this is, you will find that now we will come back to the alpha and the Poisson's ratio. Okay, now what is 1 by alpha? In the initial starting of this video, I have explained that in equation 1. Okay, I have told that it is nothing but what? 1 by alpha is nothing but y. Okay, do you remember? I told that y is equal to 1 by alpha, isn't it? Okay, that it is related to the strain per unit stress. So stress will go to the numerator. So this is nothing but stress by strain again will be equivalent to y. Okay, so this relation is y. Okay, see your equation 1 and 2. Okay, and this will become this, and this will get cancelled out. So it will become 3 into 1. No, It will become 1 minus of 2 into beta by alpha is what? Do you remember the equation 2? Beta by alpha is nothing but Poisson's ratio sigma. Okay, this also I put it in the equation. Okay, in the beginning. Okay, so beta by alpha, I will take it as sigma. Okay, I will write it down. Okay, one more time. 1 by alpha is nothing but y, and this is 3, and this will become 1 minus of 2. This factor is nothing but the Poisson's ratio as sigma. Okay, so I have connected now. The on this side is what? Yeah, this side we are having bulk modulus, isn't it? Okay, bulk modulus is given by this equation. So bulk modulus is equal to K is equal to Y divided by 3 of 1 minus 2 sigma. Okay, is that clear to you? So this is a relation that will connect the bulk modulus, Young's modulus, and the Poisson's ratio. Okay, we have arrived at the end of this definition. So initially we started to derive the relationship between the Young's modulus, bulk modulus, and the Poisson's ratio. Okay, I explained the relation of alpha and beta. What is alpha and beta? I have explained, and then how alpha and beta are connected with Young's modulus. You're seeing this relationship. How the beta and alphas are connected to the Poisson's ratio. We started with the Poisson's ratio, and we related the Poisson's ratio with the Young's modulus first, and then we considered a Q with a unity area, and then we have applied the force along the X, Y, and Z direction. And then we got 3 equations, we multiplied, we find the new volume, okay, and then we subtracted with the initial volume, and the increase in the volume of the cube has been taken as the strain factor, and it was put up over here. And then the bulk modulus value is connected with the Young's modulus and the Poisson's ratio in this way. Okay, so I hope you are able to understand. Slowly go through this video, and I will send the book notes also, so that you will be able to understand it more clear and try to make the notes. Okay, thank you so much for listening to this class, and we will conclude this section. Okay, thank you so much.